Alright, so hey, welcome to another video on the Embedded Systems series. So today we're going to be looking at one of the more important concepts, at least I consider it to be one of the most important concepts in embedded systems, which is interfaces. So what do I mean when I say interfaces? Well, I have an example, if you entertain me. Think USBs. I have right now a USB device in my hand. It's a mouse. And this particular mouse, the Logitech G203, well, it was developed and put into production, sent to stores, and I've bought it and connected it up to my computer, and it just worked. And maybe the developer of the operating system I'm currently running, which is Linux, maybe they knew the existence of the G203. However, I certainly think they don't know of every mouse in existence, but somehow they all work, and this is thanks to standardization. So that's, I think, one common thread we'll be talking about, this idea that if we standardize an interface, in this case the USB connection, then we can sort of develop our hardware, implement the interface, and then things will just work. Trademark, that's something thrown a lot in the industry, just writing software that just works. In this case, we're developing hardware that just works. And I have a little comment here, the zero knowledge interface. So a little idea that might convey this concept is maybe the developer working on the USB interface in Linux, maybe they knew of the Logitech G203, the mouse I'm currently using, but they certainly don't know of future mouses that are going to come into existence. And when I connect any mouse, the operating system, Linux, Windows, or Mac, doesn't know what I'm going to plug in next. And effectively, they have zero knowledge of what they're interacting with beyond what they'll be receiving through the protocol. And this idea that we don't have to have knowledge about the hardware we're interacting with is very powerful. It lets us create basic building blocks of software that we reuse throughout our projects. We have one implementation of the USB mouse in protocol in our Linux kernel, and it just works with every mouse. And this will be an idea I'll be sort of revisiting throughout this video. Next up, it's the HAL, or HAL, aka Hardware Abstraction Layer. This is a term that's I think I've most commonly heard about it in C SDKs, C the language. One could think about it as the layer. Again, I'm saying layer, but I don't think it's very. So let me just create a new example document here. When I say hardware abstraction layer, I'm talking about code, right? And more specifically, I'm talking about maybe a function, the idea of a function. Set pin a function called setPin that takes in a Boolean value and returns nothing. And C SDKs tend to do this, where they define a function that the user must implement. So let's think of the example of a device that connects us to Wi-Fi. So this can be a little chip, an integrated circuit, which might be in a laptop, it might be in an Arduino. You might hook it up via an Arduino or a Raspberry Pi. Anyways, so there's the developer of the library of interacting with this Wi-Fi. They know that to interact with this Wi-Fi peripheral, you need a pin that can set a high voltage and a low voltage, and that will let you talk to the pin and control it. Maybe it's an SPI connection, like we've seen in a previous video of this, the SX1278 Embedded Systems 101 video. So touched on the SPI, and we did see a bit of this abstraction. So the developer of this Wi-Fi chip driver, they need the user of the library to implement this setPin function, which sets the chip select pin for the SPI connection, for example. Now, the developer of the library doesn't know where this code will be running. They only know that there has to be a pin. So really, the developer of the library is not going to put any code inside of this setPin function. It's just going to be just a floating function, an abstract function that, hey, we'll tell the user, hey, you need to implement this setPin function to interact with my Wi-Fi device. And so this is what the whoa, looks like my phone thought I was calling out to it. So the user, the developer of the library will say, user, please implement this. And this is what the developer of the library says. And the user replies, okay. Okay, and they say, well, setPin is equal to, if we're using something like MicroPython or TinyGo, we'll use the machine package, and we'll use a GPIO12.set function. Whoops, try to save it there. So we'll define for our use case. If I'm the user, I know how I'm connecting this this peripheral, and I know I'm using my GPIO 12 pin. And the set is a function, right? So this is how we would implement it, speaking very abstractly, right? This is not actual code. This is pseudocode. It's not any particular language. And so once we implement this, the hardware, the abstraction layer, which is, I guess if we're trying to pinpoint where the hardware abstraction layer is, it's this right here. This is we sort of implement the hardware abstraction layer. Sort of the whole. This is the concept of the. This is the concept of the hardware abstraction layer. Sorry, sort of went into a loop there. Hopefully you sort of understood it. I'll keep talking about this throughout the video, so even if it wasn't exactly clear, we'll see it during the example. So up next, why do I think it's one of the most important concepts in embedded systems? Well, good question. I'm pretty sure that most embedded systems engineers can agree that we want to write software that not only works, but we also want to write software that's reusable. We don't, at least I don't want to write. I find it very fulfilling to write software that not only solves my current problem, the problem I'm having today, but also solves future problems I might not even know I'm going to have. And for me, that's very attractive. So that's why this really calls to me, and there's lots of other reasons. We'll touch them up towards the end of this video. And there's I've left a note here, simple API, powerful abstraction. What does this mean? What does this philosophy mean? So when I was talking about USB, I did say, so this idea of standardization, having a standard which governs everyone interacting within the USB spec. Standards and APIs can be thought of being very similar, just rules. Standards are rules, and an API is also a set of rules. Hey, your driver needs to implement these functions to fulfill the API, and well, that's just what we saw with this hardware abstraction layer. It all ties in. And the simpler this standard, this API, the more powerful it becomes. Arguably, this is again right now I can only state it as an opinion, though I think there's a lot of people who would agree that the simpler like the API, the easier it is to work with, easier it is to reason about, test, and just overall work with. So that said, let's get into the code. So I've got a little example we'll be working with. It's this Morse code example, and I already developed a little library for it, for using it, and it's right here. This is the Morse library. In case you're not familiar with Morse, let me just recap what Morse is. So back in the day, in the 1800s, we did not have the way we communicated across large distances were telegraphs. So what you'd have was maybe a telegraph station in Europe, a very long cable that went underneath the Atlantic Ocean and surfaced somewhere in the USA. And on both ends, you'd have a telegraph, right? And in each telegraph station, there'd be an operator sitting with one of these, and all they could send was a pulse. So you'd press this button on the telegraph, and someone on the other side would receive it. Maybe they were wearing headphones, and they'd hear the beep of you pressing the button, and they'd know how long you pressed it. And that allowed us to send messages, text messages. This would be the original internet, if you will, where instead of HTML, we'd send text as beeps. So A was the letter A, we'd encode it as a short beep and a long beep. And these were dots and dashes, right? And letters would be separated by a period of silence as long as a single dot. sorry, not as long as a single dot. As long as 3 dots, was it? We'll see. And well, this was the main method of interchanging information. And I've implemented sort of this functionality here. So we have our pin type. This is a function we must pass into telegraph when we define it. So a telegraph is defined by a dot, which is the time duration. So this would be how long we want our dots to be, and a pin. And as I've just mentioned, the pin is a function, and as you might probably guess, this is the hardware abstraction layer right here, working its magic. We instantiate a new telegraph with this pin function, which we don't know what form it has. The user is going to find the pin function, and they'll use this telegraph with their own specific pin type. So the way this pin type works is when it receives a true value, it's like as if the telegraph operator started pressing the button, and when this pin function receives a false is when the telegraph operator stops pressing the button on the telegraph. And with that, you can already implement a whole telegraph system. You can send messages, encode them over the pin. And well, if we're going to go into some sort of depth, we can look at, well, we convert all our characters to uppercase. So Morse code only works with, does not have cased letters. They're all uppercase, if you will. We have our Morse table, which we convert the character to the code. If we go to Morse table, you'll see there's dots and dashes for each letter. And if there is no code defined for that letter, we just ignore. So we'll only be able to transmit ASCII characters and space. ASCII characters in the alphabet and spaces. And this is where the actual setting of the pin happens. So if it's a letter, we start by setting the pin to true. If it's a dot, we wait the dot duration. If it's a dash, we wait 3 times the dot duration. If it's the space, we wait 7 times, because we also add this dot here. After we're done transmitting the dot, we let go of the dot or the dash. We let go of the pin, and that's pretty much all there is to the Morse to the telegraph. So let's go ahead and implement it for using an LED. So here I have a blank program. Now I will be using the Raspberry. It's not a Raspberry Pi product. It's a Waveshare 0, which has a colored light. So let me just start recording on my camera, so I can show you what we have, what we're working with. This is the Raspberry. This is the Waveshare 0. It's got a little LED light right there between the buttons. As you can see, it's the same microcontroller as the Raspberry Pi Pico. So so we'll be writing programs for each one of them and seeing how reusable a program can be. So I'm going to go ahead and connect this, and this already has a program in it. Let's ignore that and cut off the recording and begin by starting writing a program for the Reusability. So this light is bothering me. So I'll have GitHub Copilot on. Maybe turn it off. Okay, so what we do here is we'll be using the NeoPixel on the waveshare. So that's a WS8. Looks like IntelliSense isn't picking up. I'm gonna go ahead and delete my old settings and reselect Pico. WS. Hey, it's still not working. So maybe my cache, TinyGo flash target Pico. Maybe that will generate my working directory, my Go root for the Pico. WS. Oh, because this is WS. Yeah, okay. Sorry. I had to. Of course, I was defining the identifier. Wasn't going to pick up the package. So that is going to be equal to WS new, and we need a pin. So I do happen to know that the waveshare has the pin 16 machine. Oh, I need WS pin machine. There we go. GPI 16. So here I'm defining my NeoPixel pin as the GPIO 16. I will need to configure it because I don't think this library configures it for you. Pin output. Once it's configured, I'm going to want to define my telegraph equals Morse dot new telegraph. We're gonna use 100 milliseconds for the dot duration, and we're gonna need to define our hardware abstraction layer here now. So before I actually write code using this LED, I'll just define a pin hal. I'll just define an abstract function for it, and for now I'll just print setting telegraph pin to B. And we're going to want to send a message, SOS, and sending sauce. Alright, so with this, I'll go ahead and connect my waveshare, and there it goes. So it's already got the old program. I will flash the new program in right now. Should pick it up. Stop blinking. And oh, right, forgot. Let's see what. So here I'm tapping into what my my little device is printing, and right now all we have in our hardware abstraction layer is just a print statement. So it's just going to print out true for when the operator is pressing the button, and false for when the operator lets go of the button. Of course, there's no actual operator here, so I'm just talking as if we were still in 1812. So I think I'm ready to implement an actual useful program. So I'm going to want to display a Morse message through the RGB RGB light on my waveshare. Let's see, and the way I'd go about doing that is here. Here going if the operator is pressing the button, then the LED will write colors. And we'll write, here I'll define red as color.rgba, red, and I don't need to find the alpha value in this case. And in Go, if you do not provide values for the fields, they'll all be 0. So that's exactly what I want for the black color. In fact, I think there's actually a predefined. Oh, never mind. This function takes in a color RGBA, so I do need to define a black color. And we'll go red. Color.rgba black. And we'll stop printing. And I think if I, whoops, wait, let's use the monitor flag to hook up to my waveshare. So maybe this should work. So there we go. We now have our waveshare that's telling us SOS in Morse code. Though the light is green and we wanted it to be red, and that's probably some issue with, if maybe not the driver, maybe it's the certain NeoPixel on the waveshare that's got a different layout in its hardware. So we'll just go ahead and implement this function ourselves. D.ws18 device color.rgba. And it seems like red and green are inverted, which means blue shouldn't change. So let me just go ahead and do that again. Right color, LED, red, and right color, LED, black. And if we flash this again, the light stops blinking, and we should get a red SOS, which I think really conveys the urgency of the SOS message. Alright, looks like that's working. Alright, so I've sort of let's see, let's look at the agenda. There's a question here, where's the abstraction layer? In case it wasn't entirely clear, the abstraction, I did talk about it, but yes, this the abstraction layer would be the concept of a pin. The pin the operator presses is abstract. We can implement it as a print, which we did at the start of this example. We could implement it as a LED, or maybe even as just a logic level, a voltage level. And how would this abstraction layer help us write reusable code? Well, let's go ahead and try to write a version that runs on the Raspberry Pi Pico and its LED. How difficult would that be, given we're implementing this concept of a hardware abstraction layer? So Pico LED, is machine.led, and we're going to go ahead and say picoled.set. This method sets the pin's logic level. That's all we want to do. We also want to configure it, or else it's not going to output anything. And so this code does not use any of the abstraction layer we've implemented down here. It's using the Pico's pin function set. And if I go ahead and disconnect my waveshare and connect a Raspberry Pi Pico, it's already got a program loaded in. I'm flashing it and stop blinking, but as soon as the program loads into the Raspberry Pi, there we go. And we can see this Raspberry Pi is printing out, sending SOS, and we're seeing the result with its integrated LED right now. So maybe, I hope this example demonstrated the powerfulness of the hardware abstraction layer. I was able to modify a program ridiculously easy to adapt to a different target, a different hardware, if you will. And yeah, so that's all there is with regards to the example, Morse code example. I'm going to take some time to talk about further benefits, like testing. So this code, the Morse package, if has no knowledge of what the pin is, what the user is using for a pin, and this lets us just test the whole package without actually having any hardware. We don't need a Raspberry Pi Pico to test this package. We can just test it by passing in our own mock pin and observing how it behaves when we use it. And you know what? I'll go ahead and just show you an example of what I mean when I say mock pin. Let's structure with a current value, and so this is really all you need to actually use this Morse package and play around with the telegraph type. In tests, we can pass in this mock pin to the telegraph to create our telegraph, and we can observe what happens when we pass in SOS, and we'll be able to. This set method will be called just like our abstraction layer function was called. And furthermore, so I did write a few other points. So it lets fuzz. Maybe if you're not familiar with fuzzing, it's a testing methodology where you pass in just random generated input, which is not entirely random because it's sort of guided by test coverage and internal program metrics. it would let us fuzz our implementation, find edge cases and weird bugs we might not otherwise encounter if we're running with hardware, or at least it would make it much easier, since fuzzing can run several million instances of the telegraph type in parallel, and we're not limited to as many hardwares as we can buy to run that. So there's also this concept of hardware in the loop and simulation in the loop testing. These are more, I guess, not so commonly referenced topics, but so I sort of paused there for a second to catch my breath. Also kind of blanked out when it came to hardware in the loop and simulation in the loop. So what is this concept of hardware in the loop, simulation in the loop? Well, it's this, anyone can Wikipedia. I don't think I'd give a very good, basically hardware in the loop is when you have your peripherals connected to your software, which is running sort of this control algorithm, and receiving direct feedback from this from your system. So real feedback, and this is commonly done when you're testing, say, a drone. You maybe want to before you actually set it out to fly and maybe break it if it's not completely tested, you might want to have it affixed to some sort of gimbal where you can move it around and incline it and see how it reacts to these external impulses, because it probably has a accelerometer and gyroscope, and you want to maybe see that the drone's interpretation of what's happening sort of matches what it's actually experiencing. So that's what hardware in the loop is, and the hardware in the loop sister or complement would be simulation. And simulation in the loop is how I like to call it. It's also called software in the loop. So software in the loop is when you don't have the hardware and you're running the control algorithm, but without actual peripheral direct input from the real world. Maybe you're generating it through a simulation, or maybe you have data stored from an actual real life test, and you're just feeding it that, and maybe varying some of the parameters, seeing how it behaves. And well, so maybe you're asking yourself, how does this relate to hardware abstraction layer? Well, the software in the loop and hardware in the loop are two sides of the same coin. When you use hardware abstraction layers, because your pin type in the case of hardware in the loop will be something more similar to what we've seen in the example. We'll have something that actually interacts with real life hardware, like this function right here, which writes a color, or the set method on the machine.pin type. And if we're using software in the loop, we'll have something more similar to this mock pin, which I've defined down here. And we can play with these, so not necessarily, or maybe we don't, we have access to some hardware and not some other hardware during development, and we can decide which parts of our system we simulate with these mock hardware abstraction layers, and what part of the system we actually use real hardware for. And that's something that's very commonly done in the aerospace industry, where occasionally you don't have a rocket test pad for every single test you want to run of your software. Maybe you have part of the whole rocket, and you have to simulate some other parts of this rocket during your software test, or maybe you're simulating the whole rocket test. But basically, this idea of abstracting away the hardware gives us a lot of flexibility in what we test and how we test it. So, although it's incredibly valuable to test with hardware, we might not always have the hardware or have easy access to it, because, well, hardware is hard. Sometimes it breaks down, and sometimes, we're lazy and we just and we can find enough bugs or important bugs by testing. And well, that's already touched a little bit on this. You can choose to develop with hardware, with which hardware, and mock out the rest of the hardware. And this last point, optimizing complex systems without hardware. Now, what do I mean by that? Well, I've been using this example of the rocket, right, which is pinnacle of technological complexity, if you will. So, what if I told you that maybe we can simulate the hardware, and okay, I'm blanking out again, but I did talk about a drone example, and in the drone example, I mentioned we can have the hardware in the loop simulation, or the software in the loop simulation, where we feed data into the drone made from past runs. Well, in cases of rockets, we can simulate a lot of external interaction and sort of generate inputs into our rocket of what it might expect during a rocket launch without actually launching the rocket. And that might actually help us to find extreme edge cases where our rocket might fail. Example, the Ariane rocket, which had a overflow bug. So, Ariane overflow bug. So the Ariane 5 launch failed because there was an integer overflow. So I think they were converting 16 bits between. There was a 16-bit integer somewhere in there that overflowed, and well, these errors, these costly mistakes, can be prevented if you can just test most of the system, at least, by just sort of simulating the hardware you don't have access to, all within reason, right? So I think that it pretty much ends what I wanted to talk about in this video. It was sort of, I feel the video was a bit jumpy at times. I'm sorry if I might have lost you at some point. I don't give these videos maybe the planning that they deserve. I'm thinking maybe of remaking this series in the future when I have more time to really sit and think. I'm still learning a lot about how to make YouTube videos, so at least hopefully it works for something. So that's all I got for now. So thank you for staying around till the end, and see you later.